Good afternoon, everyone, and welcome to today's webinar, which is part of the ongoing series hosted by our project, CELLAR. And it's actually the last one we'll be doing in this series. Today's focus is on lessons learned during the project, some insights from the work performed related to energy communities, validation cases, and so on. But before we go into that, we'll begin with a brief introduction to the project for those who may not be familiar with it. I see a couple of people. Following that, we will continue with the core of the webinar and have 3 presentations from 3 partners of the project. We'll have a presentation from Sandrine from EDF on the impact of energy communities on the European Union energy system. Then we'll follow with a presentation from Umberto from EDP on the local energy community self-assessment tool that will be available on the platform of CELLAR. And we'll close the presentations with a presentation from Christine and Rina on lessons learned and feedback from the validation cases of the project. So, without further delays, I will start with a brief introduction. So first, some general information about the project. It had a duration of 42 months. It's actually finishing this month. 31 partners, 9 million budget, and it started in June 2022. We have 9 validation cases for which I will talk a bit more later on. So 31 partners from 15 countries around Europe. The consortium is multidisciplinary, complementary, which is needed to achieve the objectives of the project. But what are our objectives? First, to empower citizens in participating in the energy transition through energy communities mainly, promote energy data exchange, moving to a decentralized data valorization and creating value from energy data, maintaining the control of the data at the level of the data provider, which is an essential data space principle. And finally, the project aims to promote interoperability by following and advancing existing standards and practices. So how we aim to reach our objectives is by creating an energy data space that will support the creation, development, and management of energy communities, a concept that the EU has put in the center of its energy transition strategy. This includes the development of validation and demonstration of a dynamic data hub, the implementation of privacy and cybersecurity by design, delivering data-driven energy services, creating a DLT-based open marketplace, and evaluating novel business models and collaborate with other relevant EU initiatives. And also, 9 validation cases are included, which is very important for our project, since it helps the process. They help the process of developing the tools and the services to ensure we are developing something that energy communities will actually use. To ensure a holistic approach and to account for different interpretations, we have energy communities from different countries, different levels of maturity, and diverse configurations and activities. You can see here the geographical locations, and here some different use cases per validation cases. So different sizes, different activities, and so on. And also we have 2 validation cases that are actually data providers that will help consume data or provide data to the platform. Here you can see potential beneficiaries from CELLAR, which since the availability of data is essential. It could be more than energy communities, could be very different and diverse set of stakeholders. And on your right, you can see the services and tools that CELLAR has to offer on a very high level. You can find different recordings of different webinars we did for each of these components on the YouTube channel of the project. So that's it from my side. So I think I will leave now the floor to Sandrine to do her presentation on the impact of energy communities on the EU energy system. So let me stop sharing.
Thank you, Georgios. Can you see my screen now?
Yes.
Okay, thank you very much. So I am Sandrine Chaussé. I'm working for EDF, which is the French big electricity company. And I'm mainly working on energy system modeling. And so I'm going to present a case study that we have done within CELLAR, which is about the impact of energy communities on the European energy system. Does it want to work? So the objective here it is not really to evaluate which will be the real impact on the real energy system of local energy communities. It's mainly to demonstrate that it is doable to use CELLAR for conducting case studies aiming at evaluating this impact, and more precisely, the impact of operating flexibilities from some local energy communities, and what are the different impacts on the power system. This we have done by combining data coming from CELLAR, from the diverse, by using some of the components shown just before, with data which have been published by other EU projects, which are about the electricity and energy power system. And these data were used in a power system model aiming at simulating the operation of the power system. So this presentation will be organized in 3 different parts. So I will first briefly explain the modeling framework and the context where are we working. Then we'll talk of the methodology of the case study and how we created the data sets and which data were used, and briefly show some results. So first thing, for conducting studies on the electricity power system in the future, we need to have some energy transition scenarios. And this we took from an EU project, which is still ongoing, called Manœuvre, in which, together with other EU projects, have been developed some energy transition pathways. So what is a pathway? It is from now until here 2060, what could happen to the European energy system with different assumptions. So on this colored figure is well, a 3-dimensional matrix with different axes with groups of assumptions. So the red axis is about the social dynamics. So this is if the people will be more or less aware of climate change, if they will more or less accept new technologies, if they will more or less align with the green policies, will they behave in order to shift to the transition. So here we will have, for instance, parameters about will the people adopt some good ways of behaving in their local energy communities, like adopting ways of managing their flexibilities, not only for lowering their own electricity bill, but also for helping the system or that kind of things. On the green axis, you have, which is called geopolitical instability. We have all the impacts of what happens outside of Europe, like geopolitical tensions and wars, which is currently very active. Everything about trades, competition, international agreements, autonomy, and so on. And the blue axis about innovation. So here we'll have assumptions about the costs of the different technologies, the efficiencies of the different technologies, also decentralization and so on. And there have 4 different scenarios have been defined there, which are those boxes. The blue one is simulating the current energy policies of the European countries, which is the NECPs for National Energy and Climate Plans, which have been published last year by all EU members. And this is the scenario that we have chosen for this study, but there were also 3 others. Repower EU++ is trying to simulate what would happen if the Repower EU plan of the EU Commission would be applied successfully. GoRes is a scenario where everything is extremely optimistic with a lot of green energy, a lot of renewable, all fossil kicked out. And EU Trinity is the pessimistic one with fossil remaining. And so we focused only on the blue ones. And those scenarios, they have been defined from 2025 until 2060. And for each year, they include, they define what is the energy installed mix. So that is which technologies will be installed and how much, what are the interconnections, and also what are the different demands per uses, like the demand for heating, for transportation, and per energy vectors. So this is what we did in this study is that we took everything that has to do with electricity in these scenarios, because not only electricity is involved. And so this is the main electricity variables. Here on the top, it's the electricity generation. So each big box is one of the 4 scenarios. So we are mainly looking at this one. And there is 1 bar per year from 2025 to 2060, and the different colors are related to the different installed the different produced electricity, and on the bottom it's the demand. So we think the demand for transportation, which is the dark blue, for electric transportation, the demand for industry, the buildings, and the other uses of electricity, like everything that can only be used by electricity. And we see the trends, which are different in the different scenarios. And on the bottom, it's the installed capacities. So of course it's different because you need to have a very high quantity of installed PV to produce much less, because as everybody knows, PV does not produce anything at night. And so we have chosen to take that's the scenario reproducing the NECPs for the year 2030. We took this one because this is what is currently decided in the different EU countries' plans And so this is, well, what everybody is hoping that will happen. Not what we believe that will happen, but anyway. So then once we have all this context, what we have done is that we have used a model, which is a power system model, which is called Plan4S. This one has been chosen because it is 100% open source. It allows to easily use public data from the scenarios. We know how to use it because we were involved in the implementation. And it is stochastic and has lots of good properties. So this model, what it does mainly, that it takes as input the installed capacity, so how much of its technology is installed, including the generation, the storages, but also the interconnections. It takes also as input the electricity demand. Also, you can feed it with some system services requirements like margins and so on, lots different kinds of reserves, and uncertainties, mainly on the renewable production potentials, on the electricity demand, on the inflows, and so on. And it simulates the operation of the power system, computing generation schedules for all technologies, but also costs. And it can also be used for investment optimization, but we only used the first part. Something else that is included in the model is this model can also be used to represent flexibility from demand-side management, and in particular, flexibility from demand load shifting, which is something that we used in the case study. So just a brief introduction. On the left, you see this curve, the big blue curve, it's, well, the reference consumption, if nothing is done in terms of demand-side management. This curve could be reduced if you would curtail the demand, that is asking people to consume less, and that is all. But what is called load shifting is moving some users from one time period to another, like taking a shower at 8 in the morning and not at 8 in the afternoon. This will increase the consumption in the morning and decrease it in the afternoon, or do the contrary. And this is modeled in the Plan4S power system model, and it can also be optimized with different sorts of constraints. And this has been used here in this case study. So what we have done is that we have compared 3 different configurations. So the first one was just simulating the power system with as it is, with no flexibility. So we took a reference consumption from the data CELLAR marketplace, and we added it to our total consumption. Well, not really added it. In the end, the consumption wasn't really changed. But this is as if we had done that. The second option is that we assume that there are some VCs in Europe that can be optimized by the consumers that are there, and that they will optimize their consumption by using the data CELLAR flexibility estimation function, running it, and this produce some optimized consumption schedules, which were fed into the model. And the third configuration is to feed the model with possibility of flexibility by the by some local energy communities and decide that the optimization will be done not by the consumer, but by the system operator. Like you have some boxes in your houses and some specific tariffs, and the system operator will send some signals, and this will lead your optimization. And this was done by using the load shifting function of the plan Perez model. Until we have compared these three configurations for a case, based on the power system in 2030 with a representation of some local energy communities everywhere in Europe. So we have duplicated one of the VCs and done as if there were many others behaving about the same. So I will, well, this is just to say where we took the data, something that I didn't say, that for the uncertainties, we have used some very recent data from the Copernicus Climate Change Service, which have been recalculated by an EU project called Cross EU, and they are taking advantage of the most recent climate projections in, well, something that's called ERA something. So it's better than it was. And we have used data CELLAR to produce the reference and the optimized consumption and in those two configurations. For this, we needed to run the function F2. So this was not done by us because it wasn't ready yet, but by Louis, which I thank very much for this. And he gave us 40 different days with 40 different optimized schedules. And we have matched them with the meteorological conditions, in particular with the PV production, in order to have something that was consistent. So this is the installed capacities country per country that we worked on. So this is what is currently more or less in the published NECPs. So with all different kinds of technologies represented, hydropower, fossil power, renewable, you have the yellow for PV, the green for wind power, some batteries here and there. And we also took the interconnection capacities also from the NECP scenario. So when it's very thick, it's something like between 5 and 10 gigawatts of exchange between the countries. So we have represented all the countries there. Some were aggregated, like the eastern countries or the Balkans regions or the Baltics. In order of simplicity, we could have not done that, but it was quicker. So this is the power demands, which were computed by using those uncertainty scenarios from Copernicus. So here we used 100 different scenarios or time series. And so well, the uncertainty is quite big, and there can be a very big difference between the scenario with high consumption and scenario with low consumption. You recognize here we start in the summer and end in the summer. The winter is in the middle. This is to help the model, which is why it's like that, because of the electric heating in Europe. And it's all the different countries. Regarding the VC, we have chosen to use the VC from FEN. This because it was one of the VCs that was more adapted to what we were doing, because there were some flexible assets consuming electricity, some PV production, and so it was reliable. We were hoping to start by this one and do some others, but due to the delays with the dashboard and the ability of retrieving the data, we only could do this one. But it is better than nothing. So in this VC, there are some flexible assets in a set of houses and PV production, and those flexible assets, they can be started at different hours instead of the hour that was the habit of the consumer. And the schedule of those assets can be decided either by the F2 function or by the power system model. And we have replicated this local energy community, because if we only had one, we would have seen nothing. And for this, we have used the results of a case study that was done in a past EU project, which was about replication of local energy communities in Europe. So it's not figures coming from nowhere, but it's not reality, and it's only one case. So the figures are not that representative. So this shows the consumption without using the flexibility function, and the consumption with using it for the 40 different days. So this was, it would have been better to have 1,000, but this would have required too much time. And we used that to feed the different versions of the model. And so, well, here I already said only one VC was tested. The scaling up is a bit rough. Another limitation is that we only represented the interconnections between countries. The model is able to represent a real distribution network, but we didn't have enough data to do that. What is done here is highly under-optimized, because we only have one very small node for the local energy community connected to the country. And so it's better than nothing. And we only tested 1 year. So this is just to show that it worked. So we have run the reference case without flexibility. We see the flows, we see the different energies that are produced. This is just an example to show that we have the schedules day per day for each scenario in each country. So this is just one summer day and one summer week and one winter week in one of the 100 scenarios. I think it's in Spain. And well, just to illustrate, I'm not going to show these results for the two other configurations, because it wouldn't be visible, the differences, because they are pretty small. But mainly what we can see is that there is an impact on the curtailment of the renewable generation. Here, those graphs, it's autumn, winter, spring, summer, I think. And it's the difference in terms of energy generated by wind power, country per country. And so here, this orange bar means that in the case where it's optimized by the model, as if it was optimized by the system operator, there is 0.1% more energy produced by wind power. And there is something more produced when it's optimized by the F2 function compared to the reference case. This means that when it's more positive than negative, which happens mainly in spring, having optimizing those flexibilities, it allows to reduce the curtailment of the wind power generation, mainly in the periods where there is more wind, and it's even more visible with the PV. It's more in the summer and the spring, and it really helps reducing this curtailment. This because the decisions of the model are to push the consumption of the flexible assets at periods where there is more sun and when the electricity is less expensive. So this is why the blue bar with the F2 function is seen there. The electricity is less costly, and so it's better for the people to use it, and it's consistent with the power system. It's better to consume when there is less sun. And this is a very good news because reducing the curtailment of the PV production, it allows to reduce the use of the fossil production because it's replaced by some PV that could not be used. And this is pretty much visible in all the different seasons. The fossil production can be reduced. So the level of the percentages shouldn't be really looked at because it's very much linked to the replication that we have done. But the fact that the bars are more on the bottom than on the top is something that is interesting. And the last thing, which is the much more visible, is that optimizing the flexibilities from those local energy communities, it reduces the need for storage. So it reduces this we have done with the investment model, asking it to invest if necessary in batteries, and with the configuration where we optimize those flexibility those communities, it needs less batteries because using this flexibility behaves as a virtual battery. And all of this, the natural conclusion that it will reduce a bit the cost because the cost is mainly the cost of the fossil fuel. And the last thing that it will slightly reduce the number of hours where we have non-served electricity, which is an average, and it's mainly in the very dense scenarios. But so my conclusion then is that it's doable. We could do it, and it's a very good thing to optimize residential flexibilities, and in particular in the local energy communities, and it has a value. I cannot tell you which value it has, but it has one. And this is it. So thank you very much.
Thank you, Sandrine. Are there any questions at this point? Okay, if you have something in mind later on, you can put it in the chat, the Q&A section. We'll continue with the second presentation from Umberto on the local energy community self-assessment tool. Umberto, you have the floor.
Thank you, Georgios. Can you all hear me?
Yes.
Okay, so I will share my screen. Just a minute.
You can see your screen.
Okay, thank you. Good afternoon, everyone. My name is Umberto Queiroz. I'm an R&D engineer with EDP, and I'm here to show you the assessment tool that we created on the scope of this project to assess the potential benefits of association of buildings into energy communities or local energy communities, or as I will refer in this in this presentation for the sake of rigorous science, renewable energy communities. Just a minute. Okay. The rationale behind this assessment tool since the beginning of the project was the major roles that an energy community can play in local markets to deploy sustainable energy consumption by the installation of local generation assets based on renewable sources, and the lack of ways to rapidly, to fastly assess the potential benefits for this kind of association. So you have a number of individuals that want to join in an energy community, and they have no idea what could be the potentials for them, not for the grid or for the market, as Sandrine beautifully explained, but for them, what can be the benefits for them. And that's why we started developing this assessment tool. Just a brief context, as I said, I will refer to these associations as renewable energy community as the European directive and the national transpositions refer. So a renewable energy community is a legal and organizational framework based on the association of energy consumers, residentials, industrial, commercial, offices, etc., 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 to collective produce, consume, store, and share renewable energy. The real innovation of this concept is the possibility of share, similar to collective self-consumption, but with some other extra features that I won't go in details today, but can be done by this entity. The main characteristics of these associations is that they have a local scope. So the buildings in the same vicinity, in the same neighborhood, you cannot have, until today, an energy community that compares more than one municipality, for instance. They are based in a local renewable energy source for the generation. They have a collective governance, so every decision must be made by the collective of the members. And they can have the possibility to provide economic and environmental benefits for the members, but not profit. It's important, this difference. An energy community was not made to have profit, but to provide economic benefits for their users. And I will explain that a little bit in the future. In the context of the project, as I said, this assessment tool has the objective to quick assess the potential benefits that a potential energy community can have if they proceed to the formation and cross the navigate and navigate into the bureaucracy in each country to form this entity. It can also serve as a guiding tool for developers of such entity. And as we discussed during the development stage of the project, in parallel with the development of the tools that are present in the data space, this assessment tool provides a glimpse of the services provided by the CELLAR data space, most specifically some of the tools for the decision support system. We also mentioned during some meetings that they both have some redundancies, which is good, so you can compare the results from one and from another. But just to be clear, the assessment tool that I'm describing here is way simpler than the tools that were developed on the scope of the decision support tools inside the data space. Okay. In a nutshell, this is a tool, so you need to provide some inputs. The tool itself will make some calculations based on some assumptions that we stated in the beginning of the development stage, and the tool will provide some outputs for the users. I will go a little bit in detail after that, but mainly if you have the energy consumed by each member, the energy that was generated, or the available area to install PV panels. I'm focused on PV panels because it's the easiest technology to estimate production. If you provide the price for the energy and the price for the capex of, for instance, installing a PV systems collectively owned by the members, and if you provide the capacity that you have or that you want to have for storage assets, the assessment tool will give you some information regarding the self-consumption of the potential energy community and sufficiency that you can have on these equations below. Basically, the self-consumption is the ratio between the energy that was effectively self-consumed by the members over the total energy that was generated inside the borders of the energy community. And the self-sufficiency, it's similar, but it's the ratios between the energy that was self-consumed by the members over the energy, the demand of the collective of the buildings. So the demand itself of the energy community. Also, the tool will provide you the energy that was not purchased from the grid, some annual savings in terms of this energy that was not purchased, and the initial investment that you might have if you want to form the energy community as you provide information as inputs, and a few others. This is the interface that a user will see when he or she downloads the package that we are just putting in the login page of the data space as we speak. On the next days, it will be available for everyone. So you must provide the location in which the energy community is located. So the tool can estimate the production. We consider that because the tool will acquire some data on public data sets for solar irradiation in order to calculate the production. And then you provide information of if you have already have local production by PV systems, you must provide the installed capacity in terms of power. And if you have a battery, you already provide information here. If not, you can have the idea to install. So you inform that you want to install PVs and storage systems, and you must provide an approximate area that you had available in square meters. I forgot to mention here in square meters for the installation of the PVs, because this is one of the information that we use to estimate the production. Then you have to select the country in which you are. For now, I can only have 4 countries because it was 4 countries in which I found the complete set of information that the assessment tool needs to perform the calculation. So it's Portugal, Spain, Ireland, and Greece, if I'm not mistaken. And also, and lastly, you need to inform the number of members of the energy community and the total, the annual consumption of each member in megawatt hour. So you insert the information, click on these buttons, and then the assessment tool will start the calculations. From now on, don't worry, you will see a lots of flow charts and algorithms, but don't worry, it's pretty much straightforward what the assessment tool will do. First, before we enter into the self-consumption itself, because how an energy community in general works is in real time, the buildings perform self-consumption, both individual or collective, depending on the assets that they have. And then the tool will see how much energy was not self-consumed to be shared among the members. The sharing is a very important concept inside an energy consumption, and the focus of this assessment tool is to provide a way to calculate the share of the local energy that was not self-consumed that can be shared among the members. And the assessment tool does it based on the annual consumption provided by each member. We have inside the tool some consumption profiles that we found for instance, in Portugal, with the DSO provides this information every year, some consumption power for a typical residential building. So we use that. For the other, we created this profile based on the data sets provided by the validation cases. And after creating the artificial consumption of each member, these and the estimation of production or the real production is inserted into this algorithm, in which in the left part it's made the self-consumption itself. So we calculate every time instance the difference between the consumption and production, and made these calculations to give energy locally generated to each building, consider if they have or not battery, depend on the information that they provide as input. And then this is the operation, the energy management at meter level in each building. They account for the state of charge of the battery, the instant values of production and consumption, and provide the needed adjustment. And here, as the main output, we have what I call shareable energy, which is the energy package, let's say, the amount of energy that can be shared by among the members in this instance. So just another information that I forgot to mention. There's some differences into when each of these activities occur. The self-consumption occurs in real time in each building, and the sharing mechanisms occur after, for instance, the billing period. That's how it works in Portugal. And to the best of my knowledge, that's how most of the countries here in Europe are using, are making the sharing strategies. So I consider that as the benchmark and the paradigm for this sharing process. So having that shareable energy accounted for each time instant, in the case of the assessment to 1 year, we proceed to the sharing itself. So this is the algorithms that control the sharing process in the energy community. So you have as inputs for these algorithms, the demand before sharing for each member, the energy or power, depending on your on how you like to work with that, available to share, the output of the previous algorithms that I showed, and the sharing coefficient. The sharing coefficient is none other than the percentage of the energy that will go to each member. And you have here a glimpse of the equation. It's a simple equation, so you can choose whichever variable that you have inside your energy community to calculate it. For instance, this variable here can be the consumption of each member. This variable can be the production of each member. You have another variable that is the investment of each member for the purchasing and installation of the assets that were installed inside the energy community. And the limit here is the imagination of the manager of this energy community. So with that, we proceed to the sharing. We calculate the share of energy for each member. We made the share itself. So we only subtract the demand, the energy demand that a building has before the process of sharing, we subtract then the amount of energy that was calculated to go to this member, and you have that demand after sharing. And this is the demand that will be effectively billed for each member. If the sharing is made according this procedure, this value should be less than the original energy demand that the member has had in the beginning of this process. So the algorithm also take into account the energy that was not shared, because the limit of the energy that can be shared for a member in a given time instant is their demand. So a member cannot have a negative demand. So the limit is 0. So if you have, let's say, 50 kilowatt hour, and the demand of a given member is 45 in that instant, the only amount of energy that goes to this member is 45, and these 5 extra, let's say, kilowatt will be accounted to be sold by the collective of the members as the entity energy community, to a local market, to a supplier, back to the DSO itself, and that depends on the possibility for each country. So by doing all these calculations, this algorithm runs every time instant. In Portugal is 50 minutes. In Spain, if I'm not correct, unless it changed, is 1 hour. If you have data set within 1 minute interval, and the DSO allows you to make the management of the energy community with 1 minute interval, you can use it. So it does not depend on the time interval or the granularity of the data sets that you have. And then after all of that, this calculation is made for the whole data sets that was created, and then the interface, the output interface can be seen here. Despite the energy management, the tool also calculate the net present value of the investment that must be made, the savings in terms of reduction of GHG emissions. It takes account for the energy that was effectively shared for each member in the time interval considered, namely, in the most common is 1 year, and it also shows the coefficient of each member in that given period. And then the manager can use that to make a decision, and also to enter the data space in which they have detailed data sets of consumptions and production for at least 7 or 8 or 9, I forgot the actual name, of the energy communities that are part of the data CELLAR, and in the future of more users that join the data space providing their data. So a manager can make a more informed decision, let's say, if it's feasible and economically viable to create this energy community. So this is the starting point. Then he or she goes inside the data space, and with the tools that is inside the data space, the manager can have a lot more information to make the informed decision of creating or not the energy community. And my final message is this tool, with a strict amount of information, it's possible to assess the potential of an energy community to unlock wider implementation of such entity in the future. One disclaimer that I forgot to add in this presentation: all of these algorithms and calculation methods are based on the work that I made during my PhD. So if you search for the thesis, the document, it's publicly you can access and see. I perform a much better work writing than speaking, so the explanation is there with details, so you can have all the science, let's say, that was used to create this tool, especially the part of the energy management. And that's it from my side. Thank you very much. If you have some questions, you can ask me now or put in the Q&A. Thank you very much.
Thank you, Umberto, for the presentation. Are there any questions?
Let me start share.
At this point, to Umberto? I guess not. So we can proceed with the final presentation today from Christine on the lessons learned and feedback from the validation phases of the project.
Hello, everyone. For people not participating to Data CELLAR, I am Christine Leroy from RINA. So this is the content of the presentation. I will just give you first an overview on my activities with the validation cases through the project. Then I will speak about the lessons learned regarding the validation case, lessons learned with respect to the developers, and finally, at the end, the lessons learned regarding the organization of such type of activities. So Georgios already presented the project at the beginning. So briefly, as explained, we have 9 validation cases that represent 9 energy communities, and we also have 2 data providers and users. The energy communities were in part urban, for urban energy communities, 3 rural, 1 suburban, and 1 industrial urban. So just to give you an idea of the diversity of the energy communities that we had. So what I did through this project, I was mainly in charge of coordinating the activities that were to be performed by the validation case inside the Data CELLAR project. So it means mostly providing data to the tools developer, testing the tools developed, and giving a feedback, calculating related KPIs. So at the beginning, we asked the validation case what they were expecting, what were the main questions they had with respect to participating to such a type of project. And from many of them, we had that, first of all, they did not know really what was a data space, how it worked, and what could be the interest for their energy community, and what would be required from their side. We also had one explaining about the data sharing that was to be performed in the future from their side. They were also curious on understanding what how could data could be a useful resource to improve their energy efficiency. And also regarding the tools to be developed, they were expecting answers to questions such as what should I modify in my way of consuming to reduce my bills, or for example, what I should install to reduce my consumption. So after the project, we had another series of surveys with the validation case, and so 78% of the energy communities were satisfied or very satisfied with the Data CELLAR project. Sorry. So I have listed the main point of satisfaction that we received from the validation case. So first of all, for them it was interesting to have this opportunity to give a value to their data that for them until this point were just data. This could help. This has helped them to increase the energy community's members about questions related to energy data and how using their data could have an impact on the energy consumption. They also were satisfied with the benefit that they could get from using the tools that were developed during the project to optimize, for example, the operation and the self-management of their assets, to also understand how data management and adopting the tools could be important for them to decide on what to install or on how to behave with respect to their consumption and so on. And also the possibility that was given to them by participating to the project to be in contact with other energy community and to hear about their experience and share their thoughts about that. So regarding the validation case in themselves, we have two main lessons learned. The first one is linked to technical aspects, because most of the validation case do not have a technical background, at least not in the data CELLAR project. And data space are very technical from the beginning to the end of the project. It is really, first of all, it is something quite new. So not everyone is aware of what a data space is and how it works. And there are a lot of technical aspects that comes in every action that the validation case had to perform. For example, what data they were supposed to provide, in which formats they should provide this data. How they can get this data from the energy community members, and how they can share it with the tools developers. Or also during the tools test phase, how they can test the tool, which are the tool that they can test according to the data that they have. What are the tools that are interesting for them with respect to their expectation, with respect to the assets they have in their energy community. Or also technical aspects such as understanding how to use the tool, understanding the results provided for the tool. So what we concluded regarding that is that in this kind of project, it is essential that the validation case are supported by technical partners inside the project if it is already envisioned. For example, in the case of data CELLAR, we had some validation case that had officially the support of some technical partners, or it is very important that from the beginning they find in their company, in their energy community, someone that will be able to deal with such a technical aspect, even if the person is not a specialist of data space, but someone that is able to understand what it is all about. So this is the first very important point that we learn working with a validation case. Another very important aspect is the legal aspect, because even if the validation case were not really reluctant in the idea of sharing data, they have a lot of questions and a lot of fear when sharing data, because they want to know why they have to share data, what will be done with their data, and most of all, who will have access to their data and for how long. So we had a partner that was Tri that helped us in dealing with these aspects, these legal aspects, and explained through webinars, through documentation, through different calls, all questions that are related to privacy and ownership, and answer to all the questions that the validation case could have. And this is also a very, very important aspect if we want to be sure that the members of the energy community will easily provide the data needed. When going to the developers side, we realized that we were really lucky in CELLAR, because we had a partner that were able, even if at the beginning it was not so obvious, but working on it, it was really, really useful. The ability, from the tool developers, the platform developers, in explaining, in providing documentation, and in simplifying the concepts that are that were in the project, and also their availability and their disponibility in providing support to the validation case, also more than what was requested from grant agreement, but they were really available to help the validation case on a one-to-one basis, because validation case all have different level of understanding the questions relating to data sharing, tool testing, and so on. And they also all have their specificities. They have different types of data, different types of assets, and so on. So this one by one call were really important. And another aspect that is very important for the tool and platform developers is that from the very beginning of the project, data should be provided to the tools developer, because all the development of the platform and of the tools is relying on the availability of data. So the sooner the data are provided, the sooner the tool developer can adapt the development of their tools to the data that are provided by the validation case, also to the needs of the validation case. And the sooner we have the data, the sooner the tools can be tested during the project, and the tools developer can then see what are the issues that can be encountered when testing the tool, that can be technical, but they can also improve their tools regarding aspects such as how to handle the tools, the aesthetics, the clarity of the contents of the tools and of the results. And this is from the tool platforms developers side. And then at an organizational level, so of course it will also speak about validation case and tools developers. We realize that it is really important to have regular meetings from the beginnings of the project between the validation case and the developers of the tools and the platforms. Everyone remain involved in the project, and all issues can be addressed regularly and can be first seen soon and also addressed. As already said, the one-to-one calls are essential in this type of project, because we'll deal with different tools that are developed and with different validation case that are providing data and developing the tools. And from survey, we performed with a validation case for them. These one-to-one calls were very useful and very much appreciated. Also, it is very important to provide webinars and workshops where we can tool developers can demonstrate with concrete examples what their tools are about. So a validation case can better understand what it is required from their side, and where they also have the opportunity to discuss and also to test, because it's by testing something that you can see if you really understand it. Another very important point is the involvement of all the partners, since we realized that, for example, some validation case that were not, that has no technical background could do faster than other validation case, or also better, since they were participating in all meetings. So being able to ask questions, to ask for help, and also being able to know the consortium and the technical partners, so to know to who they have to ask questions and so on. And of course that, and this is valid in any project, the more you participate, the more you feel at ease with the partners, and you feel at ease in asking questions that without feeling ashamed of. And so I think that personally, I think that really the being involved in this kind of a project is very important, because there is a strong need of collaboration between who develops and who will be the user of the platform. And as already mentioned before, the availability from developers has also been very important to reach the results, because they dedicated more time than they were supposed to do to deal with any situation, any questions that the validation case have brought to the light. And that's all for me. If you have any questions, feel free to ask.